30 seconds only. Okay. Good morning, all of you. From 6th September 2019, when we had a packed house here, till today, 6th September 2020, life has changed immensely. We have experienced unprecedented kinds of changes in past few months, which has forced us to have a almost empty room to deliver to have our 11th foundation day. That notwithstanding, I'm sure since this webcast is being arranged, I'm sure people all over would have logged onto the website and witnessing this observation. Normally, going by the convention of NISER, the Foundation Day is basically a two-pronged celebration where we generally invite a scientist of eminence to deliver a general lecture. And also, we organize to give away cash awards to our semester and year toppers. But unfortunately, due to the prevailing circumstances which are beyond our human capability, we are not able to organize the second part of this. However, I'm sure given the first opportunity, we will try to organize a similar kind of function wherein the meritorious students, the deserving candidates will be given away their due. So what we have for the day is 2 in-house lectures. We have 2 speakers from NISER. So let me introduce the first speaker of the day. He is Professor Vedangdas Mohanty, who specializes in experimental high-energy physics. Is a doctorate from IOP Bhubaneswar, and to his credit, has a lot of academic accomplishments, including the prestigious Santiswarup Bhatnagar in 2015, and many prestigious fellowships from the academies like National Academy of Science, Indian Academy of Sciences, National Academy of Sciences, India, and Jesse Bose Fellowship of the Department of Science and Technology. So without taking any more time, let me invite Professor Vedangdas Mohanty for his Foundation Day lecture today. Thank you so much.
Okay, good morning, and thank you for giving me this opportunity to talk on this occasion, which is the Foundation Day of the Institute. It is indeed a rare honor to become part of the list of eminent speakers who have spoken earlier. So I really thank you for giving this opportunity. So the title of my talk is Quark-Gluon Plasma, the perfect and the most vertical fluid. So in today's talk, I will explain each of these 3 terms, Quark-Gluon Plasma, perfect fluid, and why it is called as the most vertical fluid. Now, the first 2 is arrived at research for 20 years, and that I will discuss. And this last topic, which is most vertical fluid, is something which we recently measured using the ALICE detector at Large Hadron Collider. We found some interesting results on spin orbital angular momentum interactions, and it was published in Physical Review Letters. There is one other facility where our group is associated, that's the Relativistic Heavy Ion Collider. A couple of years ago, we also, along collaborators, looked at this aspect at RIC, and that got published in Nature, and it turned out to be in the cover page of Nature. But I will start today with something very general. This is to do with the evenings at NISER. You can see that this is the photograph of an evening sky in NISER, taken by one of our colleagues in School of Mathematical Sciences. He keeps on capturing different moments at NISER, and it's sure a record of the evolution of the institute. And I will be talking about evolution of universe. I'm really thankful to him. It's a beautiful picture. You can see that the sky over NISER is very clear, and that aspect is utilized by our science activity clubs to invite young minds, young school children, college children from Jatni and Bhubaneswar to come to our campus in the evening, in the night, look at the sky, use our telescopes. There are two such telescopes purchased by NISER. One is 8-inch, another is 11-inch telescope. And we have about 15 other telescopes which we acquired because we hosted the Olympiad for astronomy and astrophysics. This photograph is just one glimpse of the excitement that you find in these young minds when they look up in the sky. And my interaction with them suggests that the first thing that they wonder is, how big is the universe? So how big is it? Let's start with our Earth. Earth has a diameter of 12,742 kilometers, and it's quite big. Earth is a special planet. Again, from my colleagues in Earth and Planetary Science, I learned it's really special. It has the right amount of liquid water for life to sustain. It has the right rock structure, what is called as plate tectonic, which maintains the carbon level such that the surface temperature is right to sustain liquid water. It has a very nice atmosphere which blocks the harmful rays that come in from sun. And it has a friendly moon which makes sure that we do not see drastic climate changes and life survives. But the most special thing about our planet is we, the intelligent human beings. Now let's move from this 12,000 kilometers to our solar system. The distance from the center of the sun to outer edges of our solar system is 150 million kilometers. There are so many zeros here that people have to now get a different unit. And that's the astronomical unit to write it properly. This is also huge. If I take a flight and start to go to the edge of this solar system, it will take me 20 years. And perhaps it will be a one-way ticket also. And this is also very unique. If you study different solar systems which has been discovered, our is unique in the sense there is nothing in between sun and the first planet, not even asteroids. That's not true in other solar systems. The biggest planet occupies somehow a space which is very different from what is seen in other solar systems. So I don't know, life is just a coincidence, Earth is a coincidence, we don't know. On a side track, it's also interesting, all the planets that we see are named after Greek and Roman gods, except Earth. Earth, it seems, derived its name from German or English word meaning ground, but all others are Roman gods or Greek gods. Now, if you are thinking, where is our position in this universe, then I take you to the diameter of observable universe and look at the numbers. It is 8.8, 10 to the power 26 meters. We are not in the center. We do not occupy the large part of it. So indeed, universe is big. Now the next question is, how did this universe start? And how did it evolve to the current stage? Well, the universe started with what is called as the Big Bang, and I will now discuss this Big Bang model, which is one of the most successful models talking about how the universe started and how it evolved. Now, what does this model tell? It tells that about 14 billion years ago, somehow the universe started with explosion of the space. It had high energy density and temperature. It expanded, cooled, formed elements, and then gravity came into picture and it drew matter to make stars, planets, and galaxies. Now, if you tell me why should I believe this model or this picture, well, it has evidences which are in support of this model. One of the oldest observationally verified evidence of expansion is the Hubble's law. What is this? This is velocity of galaxies plotted along y-axis as a function of distance of the galaxy from us. And what you see is that the galaxies which are farther away are moving fastest, and the galaxies which are closer to us are moving slower. Universe is expanding. Support of the Big Bang model. The second interesting support of Big Bang model is abundances of light elements. Now, what do I mean by that? Now we know, due to this model, that there are two ways by which nuclei have formed in this universe. Nuclei which are light, like deuteron, helium, lithium, they got formed when the universe was few minutes old, or when it was hot enough. And then it expanded and cooled. But those heavier than helium got formed in the cores of stars. What this model tells is this relative abundances of light nuclei depends on the baryon density. Now, what is baryons? Baryons are particles like protons. They are, I will come to it, they are three quark-carrying objects like protons and neutrons. So the abundance is dependent on the density of baryons. That's the key point. And whatever densities, whatever abundances they predict, that's what we see. 15% of the universe mass is helium, or 0.01% is deuterium, and a small fraction is lithium. That's what we see. So second evidence of success of Big Bang model. The most landmark evidence is it says you should see cosmic microwave background radiations. Now, what are these? When the universe was young and it was very hot and dense, that time we did not have atoms. They were all melted into protons and electrons. And these being charged particles, the interaction is electromagnetic interactions. That means the interaction which is mediated by photons. So the photons in the system got scattered, kicked around by the protons and the electrons, and continuously getting scattered. When the universe cooled and atoms formed, photons decoupled. And since then, they have been traveling to us, and as the universe is expanding, they're getting fainter, lower in energy, and this is the intensity of those photons as a function of frequency. This is what is called as the cosmic microwave background radiation. It's a perfect black body radiation. Can fit it to Planck black body radiation formula, which you have read in quantum mechanics or modern physics. And you can extract the current universe temperature to be 2.7 degree Kelvin. So these are the evidences that this model works, and that is how universe is formed. Now let me take you to a closer look at the evolution of this universe. And this is the evolution of the universe. And this is also increasing in time. And it's increasing in temperature, decreasing in temperature, system is cooling as some work is done to expand. And I would draw your attention to the first title of my talk. I'll draw your attention to this microsecond old universe, which has temperature of the order of 10 to the power 12 degree Kelvin. Here, you see the quarks and gluons are free. What are these quarks and gluons? These are the fundamental constituents of which matter is made up of. For example, protons, neutrons that you know are made up of quark and gluons. We are all made up of quark and gluons. That's the basic unit. Even the cell that you study in biology is made up of quark and gluons. This is the most fundamental, so far, constituent of any matter. And it's free. It's in a state of plasma, and that is called as Quark-Gluon Plasma. Microsecond old universe, temperature of the order of 10 to the power 12 degree Kelvin, had this state of matter. In nature, that at the moment you do not see free quarks and gluons. So you cannot study its properties. So our goal is to create a similar state of matter in laboratory and study its properties. Why? Because we want to know what are the properties of the matter which each one of us is made up of. So that's the Quark-Gluon Plasma. Remember, it existed in a microsecond old universe and temperatures 10 to the power 12 degree Kelvin. Now, can we have a Quark-Gluon Plasma in the laboratory? And what are the issues and what does the theory tell us? Now, let me first discuss why it's such a difficult task. Let's come back to the structure of atom. You all know atom consists of electrons, and then there is a positively charged nucleus. Nucleus has protons and neutrons, and inside the protons and neutrons are forever confined the quarks and gluons, which are the fundamental constituents of each of us. No free quarks are seen. Now, how do we free them? So let's come to the theory. What is the potential that exists between, say, two static quarks separated by a distance r? It has two terms. This term is something which you are familiar, Coulombic interaction, right? Interaction between two charged particles. Potential goes as 1 by r. And quarks carry a fraction of the charge carried by electron. So that's the term. And then there is a linear term. This is the term which is responsible for confining the quark inside particles like protons and neutrons. Now, the interaction that they do is strong interactions. So let's see what does the theory of strong interaction tells us. What happens to this potential as you increase the temperature of the system? This is the potential as a function of the distance, and this is generally leading to confinement. You go on increasing the temperature, you can vanish this term. So quarks and gluons will be free. So the idea is heat matter to high enough temperature, matter melts into its fundamental constituents. How high is that temperature? So we did some measurements and compared it to theory of strong interactions. I will come into more about these experiments and measurements later, but just to show you, this is energy of colliding heavy ions. I'll come to that in next slides. This is measured susceptibilities of the system. This is calculated susceptibility. The red points are measurements which we did. The theory is the calculations which we did. And you can see there is excellent agreement, and this result tells us that you need a temperature of the order of 10 to the power 12 degree Kelvin to melt matter into its fundamental constituents. Remember this temperature? That's the temperature in the early universe where the quarks were free, quarks and gluons. So matter, when heated to extreme temperature, will lead to formation of Quark-Gluon plasma. So what's the idea? Then the idea is you have a matter, you somehow try to heat it to 1 trillion degree Kelvin, and you form what is called as Quark-Gluon plasma. But how will you heat this matter? Because the very idea that the matter will not exist in its current form. So you cannot heat it like you do in ordinary experiments. You have to find a different way because the matter won't exist. It will melt into its fundamental constituents. How to do this experiment? Well, the idea is that somehow try to pump in lot of energy in a small volume. Increase the energy density. And you know from Stephen Boltzmann law that energy density is related to temperature, 4th power. So if you go on pumping lot of energy in small volume, maybe you will reach high enough temperatures and you will melt matter to its fundamental constituents. How do we do it? We collide heavy ions at very high energy, relativistic speeds, 0.999 times speed of light. Pump in huge amount of energy in small volume. Energy density is large, temperature will be large. That's the idea. 2 facilities currently running is the Large Hadron Collider at CERN. It's an accelerator complex with 27 kilometer circumference. And then the relativistic heavy ion collider at Brookhaven National Laboratory called RHIC, R-H-I-C. And I wanted to show you this, see how technology has improved. I always, when I see, I get fascinated. This is a Google picture of the facility where I work. And this is the RHIC ring. It is 3.8 kilometer circumference. The very fact that it is smaller compared to LHC tells us that the energies are also different. This is colliding heavy ions at higher energies, about 20 to 25 times larger than at RHIC. So the idea is collide heavy ions, pump in a lot of energies, expect temperature to go large. You have a free system of quark and gluons represented by these colored objects. Quark and gluons carry color quantum numbers. And then from these collisions, you will have a lot of particles produced. Each track here is a charged particle on my detector. And you try to reconstruct the entire event and then see if you formed a quark-gluon plasma and can you study its property. That's the basic idea. So, but the greatest irony is the following. The system that we are talking about is femtoscale, 10 to the power minus 15 meter in size and also in time. But the detector that we have to build to capture it is several meters. 10 to the power femtoscale system to detect it, meters of scale detector. And this is the Alice detector. Just to give you the relative size, this is normal human being size, and this is the detector. If you take a cross section, this is a normal human being sitting inside the Alice TPC, the main heart of the experiment, which detects all kinds of charged particles, and that's the size. Okay. That is not only the challenge is this experiment produces many different kinds of particles. It's energy getting converted into mass, and different kind of particles have different masses. These particles differ in energy, charge, mass, lifetime, the constituents, and the way they interact with matter. So you have to have many sub-detectors. Each has to have a special material to capture these particles. Suppose you manage to do that and build this, you have to tell the system when two heavy ions collided. They are colliding at relativistic speed. So you have to give a trigger to the detector to tell, okay, collision happened, start taking data. These are not living beings. Even if you manage to do that, you have so many kinds of detectors. So you have to have innovative ways to coordinate this data so that you can combine everything together to construct one event. So you need data acquisition system of proper type. Each collision, the collisions lead to data which are hundreds of terabytes. You need to have place to store that data, process it, and then do physics analysis on it, and then get the results. All these leads to people who have to be involved in all these areas of physics. And hence, it's a truly interdisciplinary science in terms of the physics. And also a single person having expertise in all these areas naturally is not possible. So we have collaborations which runs into hundreds or thousands. That's the reason we have to put together people with different expertises to do this. Okay, now that I have told you about the experiment, now let me try to convince you that we have reached temperatures 10 to the power 12 degree Kelvin. And we have formed Quark-Gluon Plasma, the first part of my talk. Now we have all done these collisions. How do I measure the temperature? No sensor will work at this temperature. How do I find? And the system is femtoscale. So we take help of statistical mechanics for a thermal system. We know that the average population of the constituents as a function of its energy is Maxwell-Boltzmann distribution. And the inverse of the slope of this distribution is the temperature. Okay, so now we know how to get temperature, but there are so many kinds of particles coming out. Which particle I will choose which will truly reflect the temperature of quark-gluon plasma? So we have to choose a particle which does not interact with the constituents of the system. Because if they interact, they will not faithfully carry the information of the temperature. Our system is a strongly interacting system. Strong interaction is one of the 4 fundamental interactions in nature. Other 3 are electromagnetic, gravitation, and weak interaction. So we choose photons which do not undertake strong interaction. It undergoes electromagnetic interaction. The time scales are different. We choose photons which come out of quark and gluon interactions and try to see its distribution. This is the yields of those photons as a function of its momentum. For photon momentum, energy same. And these are the results from 2 gold nuclei colliding at center of mass energy 200 GeV. Even if I have measured it, how do I convince people that there is something different? We have formed quark-gluon plasma, so we need to have a baseline. If something is above this baseline, I say, okay, that's the physics I saw. So what would be the baseline? Now remember, 2 nuclei colliding is a bunch of protons and neutrons. So the baseline naturally is 2 protons colliding. 2 protons colliding will not create enough energy density to form quark-gluon plasma. So I need to compare my distribution to nucleon-nucleon or proton-proton collisions. So we made measurements with proton-proton collisions in the same facility. This is the data. If the nucleus-nucleus collision is a simple superposition of many proton-proton collisions, then this is what we should get. We got enhanced yield, photons being radiated from quark-gluon plasma. Distribution is exponential. The slope gives me temperature. Temperature is of the order of 300 to 600 mega electron volt, 10 to the power 12 degree Kelvin. So we did melt matter into quark-gluon plasma. We reached temperatures of 10 to the power 12 degree Kelvin, the temperature which existed in a microsecond old universe where also the quark and gluons were free. Just to give you a perspective of the temperature, this is the temperature which is the lowest recorded in the laboratory. This is the temperature 10 to the minus 6 degree Kelvin for trapped ions. This is happening or being attempted in Ashok's lab, something similar. This is the temperature of the universe, 2.7 degree Kelvin. This is the temperature of this room, roughly 300 degree Kelvin. This is the temperature range from the solar surface to 1,000,000 degree Kelvin at the interior of the sun. If you did a thermonuclear explosion, you will reach temperature 10 to the power 9 degree Kelvin, and what we reached or created is the hottest matter in the laboratory, temperatures 10 to the power 12 degree Kelvin. Okay. Now that we have formed this fundamental matter which all of us are made up of, let's try to study its properties. But what property should we study? We are interested in emergent properties. This is an idea borrowed from condensed matter physics. Basically, we want to do condensed matter of QCD, which is the theory of strong interaction or quantum chromodynamics. What condensed matter physicists do, I'm not an expert on this, but I'll try to say what I understood. They try to change the doping of material, the holes and electron combinations, they change, and then they try to find out the properties. How do they find out the properties? They shine light and study the scattered particles. This is what is called angle-resolved photoemission spectroscopy. You change the doping, use these techniques, and try to see what phases you get, and then you get emergent properties as strange metals. Can we do the same thing for strong interaction? This is quantum electrodynamics, QED. Can we do the same thing in QCD? This is temperature, this is baryon doping. I can change the number of baryons that I put in a system by changing the collision energy. And I want to study the scattered particles which fall in my detector and try to see if I see any emergent properties of QCD. Okay, so first thing that I will discuss is viscosity. Now we all know what is viscosity. Viscosity, we all know that honey is more viscous than water. So what is viscosity? It is resistance to flow. And we have all come across this formula in our school or college times. Force per unit area is proportional to the velocity gradient for the fluid. The constant of proportionality is called as shear viscosity. Now, if you want to compare viscosity across different fluids, you have to take the density into account. So what people do is compare what is called as kinematic viscosity. Okay. Do you know that there is a quantity like pitch, which you use in roads? It is 230 billion times more viscous than water. It's a very interesting experiment is going on since 1927. In this conical flask is pitch, and there is a beaker. And what they're trying to see, how long it takes for one drop to fall into the beaker. And since 80 years, only 8 drops have fallen, and never anyone has seen when the drop actually fell. It takes enormous amount of time there, and suddenly it falls, but nobody was in the lab. But of course, they have mass to measure that one drop has fallen. Okay, and now of course there are CCTV cameras. This is still going on, 8 drops have fallen. I will take you to the other limit. What is the minimum viscosity a fluid can have? Is there a bound, or it can be 0? Well, Maxwell said that for dilute gas, shear viscosity goes as 1/3 times the number density, momentum, and mean free path. Now from uncertainty principle, Heisenberg's uncertainty principle, you know momentum and length scales should be greater than equal to h bar. We will talk about kinematic viscosity. So we will talk about a quantity eta by S. S is entropy density. Statistical physics says it should be Boltzmann constant times the number density. Immediately you substitute and you find eta by S, kinematic viscosity, shear viscosity to entropy density ratio should have a lower bound. But that's not the complete story. These three people came up with the lower bound from string theoretical point of view and said that there should be a bound for strongly coupled systems. Eta by S should be greater than 1/4 pi in natural units, modulo some corrections, but this is the bound. If you have a fluid of eta by S around 1/4 pi, it's the perfect fluid. It's the fluid with the lowest viscosity. It would be an emergent property of QCD. So what we did, we tried to see what is the viscosity by entropy density for Quark-Gluon plasma. Remember, the fundamental matter we all are made up of. We tried to devise observable which measures the flow. Viscosity is resistance to flow as a function of the momentum, and these are blue are the data points. Of course, this is reflective of the flow of the Quark-Gluon plasma. Now we want to extract viscosity, eta by S. So we have to compare it with theory. So we have to do relativistic hydrodynamic calculation, because that's the theory which describes the dynamics of flow, hydrodynamics, flow of fluids. This is the equation. This is nothing but energy momentum conservation equation. We have to solve it. What is this? This is called as the energy momentum tensor. It is a 4x4 matrix, 16 components, but it's a symmetric tensor. This T mu nu means it has a flux of mu momentum across a new surface, or roughly it means momentum per unit time per unit area. Now, if there is no viscosity and no conductivity, all the diagonal elements in this matrix are 0. If there is, then those terms will appear. So what we do is we solve this equation with viscosity to entropy density as a parameter. If you have eta by S 0, this is what we get. If you have eta by S 1/4 pi, remember that's the lower bound, this is what you get. 2/4 pi, 3/4 pi. You see, viscosity reduces the flow. That's the right trend. And the flow that we observed is pretty close to 1/4 pi. So if you compare it to any other known fluid, viscosity implies fluid imperfection as a function of temperature. This is where water lies, helium lies, cold atom lies. Order of magnitude below is the flow of the fluid that we created, fluid of Quark-Gluon plasma, the fundamental constituents of any matter. It's a perfect fluid. Eta by S between 1 to 2 times 4 pi. Now, let me move to the third part of my talk, which is to do with spin orbital angular momentum interactions. Angular momentum, all of you know. I will tell a few words if there are some students out there about spin. Spin is also a form of angular momentum. Let's go to particles like electron. Electron has a spin half. It can have 2 states, up and down. There could be particles which have spin 1. Now they can stay in 3 states, -1, 0, 1, the Z component. Spin is a fundamental property of the particle. It could be zero. It's an intrinsic property. It's like a charge and a mass is a property of a particle, like that it's spin. And when you do experiment, you see experimental manifestation of spin. And if you do a theory like relativistic quantum mechanics as formulated by Dirac, then you will also find spin coming there. So that is spin. And this is orbital angular momentum. And this is the spin-orbit interaction, which plays very important role across different areas in physics. It's responsible for fine structure in atomic physics. Okay. By the way, there is an interesting anecdote related to spin. So Unfest one day, sometime in October 1925, wrote a letter to Lorentz saying that 2 of my PhD students have found a witty idea about what is spin. I want to discuss with you. Lorentz's response was delayed, but when he responded, he said, very nice idea, but inconsistent with classical electrodynamics. Then Uhlenbeck, one of the students, the other was Goudsmit, he ran to Unfest and said, please don't submit the paper, it's all wrong. Then Unfest said, oh, I have already sent it. Then he said, but it's wrong. Then he said, no, your idea is nice, it may be wrong, but you are also young. What reputation you have to protect? So let it go. 2 years prior to this, Kronig, Columbia University PhD student, had the same idea. He ran to Pauli and said, I know what is spin. Then Pauli said, very clever idea, nothing to do with reality. He didn't publish it. So the credit of spin went to, thanks to the supervisor who could understand and allowed the student to pursue his idea, and that's how they are credited with discovery of understanding of spin. Spin also plays an important role in nuclear physics. The cell structure, the cell model of nuclei depends on it. Now it's very difficult to visualize that protons and neutrons will also have the same cell-like structure as electrons have in atoms. You know, you can take electron to any orbit, nucleus has a finite size, and protons and neutrons are inside a nucleus, they should be moving around. So very difficult idea to visualize. But then when people plotted the binding energy of nucleons as a function of mass number of protons and neutrons, they saw strange peaks. That means large binding energies for specific values of number of protons and neutrons. These peaks means more stable nuclei. These are called as magic numbers or magic nuclei. And that led to this, and people found out this spin-orbit interaction role. And whenever I happen to attend the doctoral committee meetings of my colleagues in condensed matter, I also always see this spin-orbit interaction. It's a key part of what is called spintronics, the new generation device. Remember electronics? Devices now based on spin. So it has a wide impact on physics across different areas of physics. I want to see what's its role in. Okay, we have a lot of particles produced with spin. Electrons, as I said, has spin half. Protons have spin half. Baryons like lambda, which has UDS quark, also has spin half, up and down, 2 states. But there are also spin 1 particles, which can have 3 states, -1, 0, 1, like K star and phi. So we have spin, but where will we get angular momentum? Angular momentum comes from different aspects here. So, angular momentum, now I'll explain that. 2 ions come to light at non-zero impact parameter. Impact parameter is the distance from the center of one nuclei to the center of another nuclei. So they are coming and colliding, and a huge torque is imparted to the system, and that gives a huge angular momentum. Now, if you use this geometrical picture, one nuclei coming, another nuclei going, they collide, it gives a torque, it gives a huge angular momentum. If you do a calculation, the angular momentum are of the order of 10 to the power 5 to 7. They collided head on, there is no torque. Angular momentum 0. Not touch each other. Angular momentum of small and 10 to the power 5 or 7 times h bar. It's huge. The highest angular momentum of a nuclei measured in laboratory is 70 h bar. We figured out that this angular momentum direction is perpendicular to the reaction plane. What is reaction plane? This is beam direction and this is impact parameter direction. Perpendicular to that is the angular momentum. This is important. I will tell you why it is important to know this direction. Now can we measure it? Okay. If you just follow simple quantum mechanics, then you can derive, it was done in 1972, 70, or around 72 to 76, I forget. I have the reference maybe. You can show that the angular distribution of the decay daughters, a particle decays into two particles, the angular distribution will have this form. Now, so for example, you have two heavy ions colliding. This is the reaction plane. This is the angular momentum. It produces a spin 1 particle. It decays into, this particular particle decays into two particles, kaon and pion. The angular distribution of one of the decay daughters will have this form. If it has spin and angular momentum, then system has, what is rho 0, 0? Now as I said, a spin 1 particle can stay in spin state 1, 0, minus 1. That means if you have a box of spin 1 particles and there is no external perturbation, then it's equally probable that it will stay in spin 0, minus 1, 1. So probability will be 1/3. Sum of the probability should be 1. So it is the probability that the vector meson or spin 1 particle is in spin state 0. Okay. Now if there is no spin orbital angular momentum interaction, then rho 0, 0 should be 1/3 because every spin state is equally probable. There are 3 spin states, so each one 1/3. I substitute 1/3 for rho 0, 0. You can see the angular term vanishes. No spin angular interaction, orbital angular momentum interaction. If I plot this quantity versus cos theta at uniform, if the spins are interacting with angular momentum, spins are aligned along angular momentum direction, they have a preferential probability. Rho 0 is different from 1/3. This term will not vanish and hence it will give a non-uniform distribution. That's what we try to measure. Do we see a uniform distribution or a non-uniform distribution? Now let's see, so what I am talking about, the analysis is carried out by that is the angular momentum. I call it as quantization axis. Momentum has to be conserved. Particle is at rest. So when it decays, momentum has to be conserved. And made by one decay daughters with respect to the angular momentum direction is. When you do that for lead-lead collisions at LHC, it's non-uniform. Now how do I know I've done right? I have to go to systems which do not have this interaction and see in the same setup, using the same detector, what I get. So we have L dot S. How can I make it 0? I can either make L 0 or I will make S 0. How do I make L 0? I will collide two protons. It will not impact this large angular momentum. I do the same analysis, same particles, same detectors, proton-proton collision, L is 0. Flat. And I can do spin 0. So I choose a particle which has spin 0, k0 short, flat. So I have seen spin orbital angular momentum interaction in relativistic QCD matter. I can fit it to that angular expression to get the probability that it is in spin state 0, and it turns out to be, you see, angular momentum 0, rho 0, 0, 1/3, spin 0 particle 1/3, for spin 1 particle different from 1/3. Probability that it is in spin state 0. We see spin orbital angular momentum interactions. What about spin half particle? Now it can stay in up and down. So we choose lambda. Lambda is a baryon like a proton, but it also has a strange quark. It decays into proton and pion. We look at the angular distribution of protons. Of course, the formula, because it's a baryon, gets modified, not like the previous one. And we can fit and obtain how much is the polarization. This is percentage polarization. This is collision energy of heavy ions from roughly 1% to 8% is the value. Now what I can do is try to find out vorticity. So I just plug in the values of the polarization. I know the temperatures, right? I showed you what is the temperature. I can get the vorticity. Now what is vorticity? Now if a fluid is moving with velocity, say u, the vorticity defines the local rotation or spin of the fluid. How do you get it mathematically? It is curl of u. For an irrotational fluid, curl of u would be 0. Remember, we can do curl or we can do divergence. So divergence of u tells us the local expansion and contraction of fluid. Del dot u 0 means incompressible fluid. So we are talking about rotation, so it is vorticity, curl of u, and if you plug in the number, 21 rotations per second. It is a fluid with such rotation never seen in nature. To give you a perspective, you know money hit us, that rotation. The tornadoes that didn't that vorticity have that vorticity. A Boeing 787 going, it doesn't create that vorticity, nor the coffee that you see when you drink causes that vorticity. All are below 1,000 rotations per second. But what we were amazed is the vorticity of this Quark-Gluon plasma turned out to be 10 to the power 21 rotations per second. Well, it is more, I just told you in a general way, it has more to it. It is this large angular momentum polarizes the spin, the quarks carry spin, they polarize it. This polarized quark hadronize into hadrons by coalescence. They faithfully carry the information of the polarization, and then that's what we measure. There is more to it. It actually has now led to development of a new field of relativistic spin hydrodynamics. I just showed you in perfect fluid, it's only relativistic hydrodynamics. Now we have to do relativistic spin hydrodynamics to understand our system. Okay, remember I started with a big bang. What we have done is a mini bang. Two nuclei coming and colliding at relativistic speed. Its spherical nuclei gets Lorentz contracted along the direction of motion because of relativity. And we pump in a huge amount of energy in a small volume, femtoscale. Temperature reaches 10 to the power 12 degree Kelvin, like a microsecond old universe. This is the Quark-Gluon plasma. It flows. It's a perfect fluid. It is polarized. It's the most vertical fluid. System expands like the universe, cools, particles start forming, and these particles hit our detector and we detect it. Is that all? Is the program over? No. We have miles to go before we have hottest matter, most perfect fluid, most vertical. But that's not the goal. The goal is to draw the phase diagram of strong interactions. We have seen indications there are two distinct phases. One is Quark-Gluon Plasma, one where the quarks are confined inside protons and neutrons. But what is the nature of this transition? Is it a crossover like ionization, or it's a first order like water to ice? Now this point is called the critical point where the first order phase transition line ends. Now note, if we discover this point, we make this phase diagram reality. Because above this point is QGP, below hadron, right first order, left crossover. I just need to discover this point to make the phase diagram of strong interaction reality. How do I discover it? Well, we again go back to history, late 1800s. Andrews, he took liquid carbon dioxide and showed if it changes temperature, transparent liquid turns milky due to large density fluctuations. This is the phenomena of critical opalescence. 1800, I forgot the exact year. So density fluctuations are the key. Number fluctuations are the key. What we can do is measure baryon number fluctuations, baryon susceptibilities as a function of energy or temperature. Theory tells me if you have a critical point, then this line is what you should see in experiment. Over last 10 years, we have been painstakingly putting 1 point on this diagram. And you can see we have followed very nicely the red part. Statistical errors on the data points are large on the blue part. And in next 3 years, the data that we'll collect will tell whether it has this pattern or we do not, this point doesn't come within our experimental phase space. If it comes, then we will have discovered the critical point in the phase diagram, and that would take my phase diagram to textbooks. The phase diagram is in the textbook. This is chapter 11, NCERT book. The underlying interaction is electromagnetism, quantum electrodynamics. That's in textbook. This is not. If we can manage to tell something which makes it a reality, perhaps one day it will go into the textbooks. So that is all I want to say, but I will end by telling students to come join mega sciences. What I told is a mega science effort, mega in all scales, starting from 10 to the power minus 15 meters to several meters, starting from hundreds and thousands of scientists working together. And actually, we are probing each part of the universe evolution. So you need not join the part which I am probing, but what I am trying to tell you is you can probe any part. If you want to find out how the universe was in 10 to the power minus 43 seconds, you can do neutrinos and you may join INO. Of course, I hope it will come soon, but neutrino, hope that. If you want to look at how the universe was between 10 to the power minus 32 to few microseconds, in CERN, or our colleagues Sanjay, Pralay, we are all working at CERN and at RIC. If you want to probe when the first nuclei started forming, few minutes old universe, join the program on facility for antiproton and ion research in GSI Dramstad. If you want to know how the first stars got formed, then that was 100 million years after the Big Bang. Then join the square kilometer array. By the way, NISER joined yesterday this program. Please contact Lytton, Nishi. If you want to know how the structure was when the universe was 500 million years old, join the 30-meter telescope effort. India is part of it. If you want how the thermonuclear fusion took place, a billion years old universe, you want to solve the energy crisis in the country, fusion process, join ITER. India is a major stakeholder here. If you want to find a few billion years holes and neutron star merged and collided, then join LIGO. And if you are interested in knowing your universe, join one of the several mega science projects which India is involved in. I'll end by listing my references. Was by Sutonu, the first one that I showed, and I would like to end by acknowledging experimental colleagues in these three experiments, the funding agency and the theorists that I learned a lot over the last several years. Thank you very much. Now, you can take this.
Thank you so very much, Professor Mohanty, for this intriguing talk. From evolution of the universe, we will also talk about evolution of NISER. Before that happens, let me invite Professor Sudhakar Panda, the Director NISER, to the dais to offer a small token of gratification to Professor Mohanty. Okay, before we move on, I was just referring to this unprecedented time that we are in. So, I mean, an empty hall of 300 capacity does not really surprise any one of us, because this has apparently become the new norm now. So, social distancing, face cover, talking to a gazette, talking to yourself has kind of become the new normal. I would like to, Professor Muruganandan, will you be okay for 5 minutes? Okay. So since, I'll take a cue from what Professor Mohanty was discussing about evolution of universe. So since we are celebrating our Foundation Day, let's also reflect back on how NISER as an institute has evolved over past 13, 14 years. Please don't ask me why it is 11th Foundation Day. Like many of us, you know, we would have a real date of birth and we'll have a certificate date of birth. So similar to that, NISER also has 2 dates of birth. There was a lot of confusion over 27 December, why that was celebrated as Foundation Day. But later on, due to a lot of factors, including convenience, since 27 December was falling between Xmas and New Year, we kind of annulled that. And 6th September 2007 is the day when the academic program technically started. So that's why it's the Foundation Day. For 11 years, we have been celebrating this day as the Foundation Day. So again, you know, referring to Professor Mohanty's talk and talking of evolution, from 2007 to 2020 that we are in right now, from a very modest beginning in one building with a very handful number of people, we have come a long way. And in the process, we have achieved quite a number of milestones, including the first batch that graduated from here in 2012 to 2014, when 2015 August, when we moved from our transit campus to this particular one. I mean, that reminds me of a very famous movie dialogue from when Harry met Sally. When you uh, want to spend the rest of your life with someone, you actually do not want to waste your time and want that time to start as soon as possible. So from the transit campus, we were also eager to move to the new campus. We could not actually wait longer. And it was August 2015 that we kind of started our movement from the old campus to the new one. And after coming here, another milestone was 7th February 2016 when the Honorable Prime Minister came down and officially inaugurated the campus and dedicated this campus to the nation. That is another milestone in the process that we have achieved. And standing here today, or sitting here today, we can only fondly recall those days. I would like to, on behalf of the entire NISER family, and of course on my personal behalf, I would like to thank all of them who had contributed in some way or the other for this institution building. So before we move on to the next talk, we have 5-6 minutes to spend. So I would like to invite Professor V. Muruganandam, who is one of the earliest members of NISER, to please come and say a few words. He would probably be able to explain the evolution of NISER in a better way. Will you be ready just in 2 minutes? Huh?
Yeah. No, but of course, I am known for giving extempo talks. If you want me to give a lecture on mathematics, now I can start. Maybe thanks to the enormous experience we had. But asking me to talk about evolution of NISER, I'm a little afraid because I would be missing many things rather than recalling. I thank Dr. Mahanti, Dr. Pranay Swain, who had given me an opportunity. Yes, of course, it's really a mammoth task. And perhaps if I am not wrong, among NISER, we are the one who first moved to our own campus. And secondly, it was a turnkey project, meaning thereby the whole campus was created, right from classrooms, lecture halls, residential complexes, everything, and with a very record duration of time. And it was indeed a great pleasure for us, for all of us. In 2015, we moved to the campus, and perhaps I was the first one to move to the campus in the sense that though officially we moved in August 2015, I have run a program, what's called a training program in mathematics, in the month of June in 2015, and we had a tough time. But of course, we are now very happy that we have our own campus and we have our own infrastructure, especially labs and so on. When I see many ISERs, actually I strongly insist my colleagues to go and see other ISERs. Then they will know that how lucky they are here, especially the building of labs, infrastructure, and so on, and also students and the beautiful campus. But of course, then Professor VC came, and he was also contributing a lot. So now Professor Panda is here. So now, of course, I think personally speaking, Professor Panda is not that lucky in the sense that the earlier director had a lot of money to spend. But now it's really a very difficult task for him to manage with the given funds which are now flowing from DAE. And also, he quickly started some more departments here, and he has a vision to build many other things like hospital and so on. And I wish him a success. And also, I wish the NISER a success in the days to come. And we are going in, I am pretty sure that we are going in the right direction. And we should work hard, especially I take this opportunity to suggest my colleagues to work hard with, and one has to improvise. In India, improvisation is very important. And I am very hopeful that things should go further, and they will certainly, NISER will certainly make a mark in the advancement of science in the days to come. Thank you so much.
Thank you so much. So from the fundamental particles of matter, let's move on to the metals in medicines and therapy. And I would like to have you a round of applause for Professor A. Srinivasan, who is a professor in chemical sciences here. Professor Srinivasan holds a PhD degree from IIT Kanpur. He specializes in bioinorganic chemistry. He was an ex-DEN research and development, and also a CRSI bronze medal winner. Srini actually wanted to have an escape, but could not successfully do it. And that reminds me of that, proverbial sentence from Mario Puzo, that when I thought I was out, they just pulled back me in. So the Al Pacino of our university, our institute, Professor A. Srinivasan. Over to you.
Yeah, thank you, Dr. Pranay, for the nice introduction. And before entering into the lecture, I would like to take this opportunity to thank the institute as well as the department chair and the department colleagues for giving me the opportunity to present today's talk. And the title of my talk is, this is one of my popular lecture. Usually go to the colleges and to give the lecture. It is most of the things are available in the internet. And I focus on the latter part of the part is mainly we focus on the things, and I will explain each and everything to how to proceed further. Today, this is the brief outline of my talk today. So I give a brief introduction about the metals, what are the metals available, and the toxicity effect of the metal. And from there, I will take out only the lead. There is the metal, which how we enter into the biological system, and where it deposits in the biological system, and finally, how one can delete the lead from the biological system. And there are famous metal positioning, which is known in the history. This also I would like to highlight. And there are metals which plays the major role for the medicine. And what are those metals and what are those medicines, which I would like to highlight today. And from there, I would like to take out only the cisplatin and focus a bit time on the cisplatin, and then move on to the contrast agent, and then finally to talk about the PDT. So this is the material which is mainly used for the treatment of cancer, and where MRI contrast agent to locate, to identify where the cancer is. And finally, there is the photodynamic therapy. One can how to remove the cancer from the biological system. So now I start with the essential element. These are the as an inorganic chemist, they love the periodic table. This is the periodic table where these are the blue color ones are essential elements which is there in our biological system. Okay. And here, these are the important metals which is there part of the biological system, where one can see a teeth and bone construction where the calcium, fluoride and phosphate, which is an important element. And if you are talking about the blood circulation, transport and storage of oxygen where the iron is playing a major role. And if you are talking about the thyroid function where the iodine is playing a major role. Okay? If there is the limit of the metal ions which is there in the biological system, if it is a 10 to 15 milligram, it should be that same amount. If it is the excess or if it is a decrease in the biological system, it will create all sorts of the problem. Okay? So this is how it plays the role. This is the metal imbalance in the biological system. So if you have the anemia, the major disease, one of the major disease, this is mainly due to iron deficiency or molybdenum excess in the biological system, where you can have the goiter, one can have the goiter if there is the iodine, if it is a deficiency in the biological system or increase in the biological system, it plays the major role for the thyroid function. And one can also find out there is the series of metal ion plays a major role for the inhibited growth. Okay? So these are the metals which is if the metal level goes down in the biological system or increase in the biological system, creates this kind of the diseases in the biological system. So from this, these are the additional metal ions which enter into the bodies. Okay, which I have mentioned about the series of metal ions which is really essential in the biological system. And these are some of the metal ions which indirectly enter into the biological system. And where the aluminum creates the Alzheimer's disease if it is on the limit crosses. And one can see this mercury where it plays the major role affect the central nervous system. And lead plays the major role for the affect the heme synthesis and affects the kidneys. And thallium also affects the whole nervous system. Fine. So from this, I would like to take out the lead, how the lead enter into the biological system. So this is how the lead enter into the biological system. Yeah, foodstuff, yeah, green, leafy vegetable soil where lead is present. Okay, or may occur during the manufacture of the product batteries and some insecticides. It comes from the batteries or insecticides. Or also exposure of to organic lead substances such as tetramethyl or tetraethyl lead from the industries. Those who are working in this kind of the area, they will have automatically they will have the high exposure to this kind of the lead, and through this it enter into the biological system. So once it enters into the, once you are having the leafy vegetable, obviously we love the leafy vegetable. Once we have such a vegetables, automatically this lead enter into the biological system. First, a lead enter into the body. Okay, it is not going to sit particularly at the things. It enters the blood and is absorbed rapidly into the blood plasma, and where it binds with the hemoglobin and other molecules. It binds with the hemoglobin. That's it. It moves around whole part of the body. Fine. Once it moves around the body, it also enter into the rest of the area. Equilibrates rapidly with the extracellular fluid. Bind the particular place and replace the calcium so that it can sit comfortably inside the body. Fine. Once it sits inside the body comfortably, this is what it creates. It will not sit silently. Okay? Once it sits silently, it creates affects the central nervous system. It also affects the cardiovascular system. How do we remove such cases? If there are try to find out where the issues are and try to delete such metal ions in the biological system. Of course, if it is not possible to identify that is the lead, definitely once we'll have the renal system issues, we will obviously approach the doctor and he tried to give the similar kind of medicines which can remove, where to solve the kidney related issue, he tried to give the medicine. Some of the systems which he usually recommends EDTA, a chelating agent which bind with the lead and remove the lead from penicillamine, where the chemically alternating the antibiotic penicillin administered orally and for the treatment of lead poisoning and excretion of the lead through the urine. So it can be removed from the biological system. Or other agents, there are DMSA or DMPS, these are all the chelating agents for lead and mercury, where the excess metal which is there in the biological system can be removed by using a simple chelating agents. These are the material which is available and where the doctor advises this kind of the material to remove lead from the biological system so that we can lead the comfortable life. Fine. Now, move on to the famous metal poisoning, history related famous metal poisonings. This is the famous Roman Empire. The downfall of the Roman Empire is mainly due to a lead poisoning, where he asked the people to install the lead pipe in the house, and where the lead, which is indirectly, it is coming into the biological system. So obviously, those who are having the upper load of the lead, obviously they will lose the life. So this is the Roman Empire downfall is mainly due to a lead. A famous Beethoven's hair is also down mainly due to the lead. And there is the violinist and composer Paganini is also down. There is the issues with the mercury related poisoning. And there is the issue of Napoleon Bonaparte is a famous history person, which is also died. There is the issue with the arsenic poisoning. And there is the disease called Minamata disease. Minamata is a bay which is in the southern part of the Japan, where the manufacturing company produces the unwanted material transferred into the sea, where in the unwanted material which includes mercury. So when the mercury enter into the sea, the fish which is lying in the sea, which is staying in the sea, take away some of, it moves around here and there, it takes some of those mercury, and from there, the fish, those who are taking those kind of the fish, automatically transfer from fish to the human being. Once it enters into the human being, where it affects all sorts of the problem and created all sorts of the problem for the people, and where mercury attacks the central nervous system and adversely affects the mouth, gums and teeth. High exposure over long period of time will result in brain damage and ultimately death. In 1932 to 1968, almost 36 years, where the unwanted material enter into the sea, where the people living around that area having that fish, they had all sorts of the problem, and almost 10,000 people died due to this Minamata disease. This is the cartoon representation. This is the cartoon representation which I would like to highlight. So this is the industry which produces unwanted material, where the unwanted material containing the mercuric salt. And there is it started a smaller phase, it started from the smaller phase and gradually increases where absorbed through eating, absorbed through fish gills and skins. And from this it entered into the bigger ones, and finally those who are having those fishes, it entered into the human being. So this is how it entered into the system, where once it entered into the system, obviously it is very difficult to follow. Fine? That creates the trouble, and that was the issue and during those periods. And these are some of the metals which can diagnose and therapeutic purpose, which I would like to focus more on that. Carboplatin is for the ovarian cancer, and lithium carbonate for the manic depression, where the gadolinium is for the diagnosis purpose, and carboplatin is mainly for the therapeutic purpose, which I would like to focus today. So these are some of the important elements and compounds in the medical purposes, where this manganese is mainly based on the gadolinium metal, mainly used for the MRI contrast agent. And there are the two kinds of platinum, one is cisplatin, another one is carboplatin, and mainly used for the anti-cancer agent. So I would like to focus first on the cisplatin, and then how to diagnose with the MRI contrast agent. And the final part of my talk, I mainly focus on how to eradicate the disease from the biological system. Fine? I will start with a simple cisplatin. So this is how the cisplatin history goes. This is started the pherone from first synthesized the cisplatin. It is called pherone chloride, first reported in 1844, and there is it went inside almost 40-50 years. There is no information about the pherone chloride. And in 1893, Alfred Werner is the father of inorganic chemist, and he first identified the structural elucidation of this compound complex. So this is again from 1893 to 1960, there is no information about this complex. So it went inside again. So there are two chemists which could not be able to find out what can we do further on this. And finally, it is 1960, it was reported by Bernard Rosenberg, a biophysicist at Michigan State University. He identified what purpose one can use it. And where effect of electrical current, he wanted to find out the cell growth of bacterial cell growth, Escherichia coli, and where he observed 300 times of normal length. And he wanted to find out what happens with this Escherichia coli, why there is the sudden increase in the length, where this effect is not due to electrical field, he is an electrophysicist, and but to a chemical agent that was formed in a reaction between the inert platinum electrode and components of the solution. It is the platinum electrode, an electrochemical reaction where the platinum electrode is one of the electrode which produces such a substances that is identified as a cisplatin. This chemical agent was later identified as cisplatin, and once it is identified, test revealed that it had prevented the cell division but not other growth process in bacteria. And to test against, first they test with the mice, it was successful, and human trials proved positive results, and finally it was approved in FDA in the year 1978. So this is the brief history about the cisplatin. So the chemistry started in 1844 and finally come into the market only in 1978. Okay? In between, Alfred Werner received the Nobel Prize. So it is our responsibility, whatever we are doing right now, We have to make sure that we have to achieve whatever we wanted to do. It is not that we have to transfer next generation to find out the issues. Okay? Fine. This is how the cisplatin goes. This is the structure of the complex, where our biological system contains almost 79% of the water molecule. Once it enters into the biological system, it binds, it replaces one of the chloride ligand attached to the water molecule. And also it is possible to replace the another chloride ligand to form the di-water complex. Fine. And where it binds, this is the guanine. We know very clearly ATGC. It binds at the guanine 7th position. It binds like this, and where it is binds only on one side. It is also possible because of the two water molecule is now out, and it also binds with the other side of the system. So this is how it goes. The cartoonic representation, this is first replace like this, and it binds on the guanine G5 position. It interacts with the DNA double helix. It binds on the one strand, and like either this or this, and finally it can bind like this. And once it binds like this, ATGC, there is a hydrogen bond between AT and then GC, and once it binds like this, it breaks the hydrogen bond so that the cell division can be died on the particular place. So the further growth of the cell can be died by clating the cisplatin like this. So DNA can be cured particularly at that particular point. So these are some of the platinum complex in addition to the cisplatin is right now available in the market. One is carboplatin, oxaliplatin, where you can see the system is remained same. 2-chloride is replaced with the carbo derivative, and then here you have oxaliplatin, you have a picoline derivative platinum complex, or also one can have a series of platinum system, something like this. These are all these complex which is right now available in the market to eradicate the one famous disease called cancer. These drugs have slower hydrolysis rate than cisplatin, and advanced head and neck cancers and ovarian cancers. Particularly, this complex can play a major role for various long-range inter and intra-strand crosslinks. It binds with the DNA in all the directions and 100 times more active than cisplatin against cisplatin-resistant tumors. Okay? So the cisplatin is having a better advantage to solve the bigger disease. Okay, now there is the possibility where we have taken a cisplatin and it eradicated the famous disease called cancer, but at the same time it also invites the various additional problems. Okay, it creates a series of side effects. An allergic reaction it takes. It also hearing loss or ringing in the ears, severe nausea, vomiting, and diarrhea, numbness or tingling, or liver damage or hair loss almost. We delete one famous disease. At the same time, we also invited a series of problems. Fine? So, how to solve this purpose? First, so what is cancer anyway? So, we are talking about cancer. So, what is cancer anyway? So, this is how it goes. In the normal body, cells grow, divide, and die in an orderly fashion. This is the routine case. And in the case of cancer cells are different because they don't die. It will not die that easily and just continue to divide and grow. If it is a normal way, it grows and dies, absolutely no problem. And if it is not die and grow automatically, that is the problem, right? Cancer cells form as a result of damaged DNAs. This is coming from the damaged DNAs. So, these damaged DNAs, it will not sit idly. It can be passed on, which accounts for inherited cancer. And in other cases, the DNA is damaged by an outside source such as smoking. And also cancer usually in the form of a tumor. So this is how it move on. It will not sit silently on one particular place. I would like to give you a kind attention on a small video here, whether it is. So what is cancer anyway? So this is the normal biological system, body, everything is there, where one can see it is, this is the routine thing. Everything is going fine, absolutely no problem. And there are, once the issue starts, then there is a breaking happen between the, and once the DNA started creating, and it will not keep quiet. It's not working. Anyway, it's okay. Huh? It's not reading. Again, open. Is that okay? Slide again. There it is. Okay, let us try whether it works. Or in this. Let us see whether it works. It's coming. Yeah. I will start again. Sorry for the interruption in between. So this is how it goes. This is the normal cell. Everything is going fine. And once there is the issue started with the DNA, it started breaking here. And once the issue started, then the cancer cell starts forming, and it will not keep quiet. And the cancer cells, it started moving around, and it binds with the lymph nodes and move on. Once it is started moving and moving, go on. Okay? It will not sit particularly on one particular place, and it goes on, and finally creates all sorts of the trouble in the system. So it is, in principle, it is what I wanted to say here. It is not going to sit particularly on the particular place. So what are the issues are there now? This is once we started afraid. Okay. So if there is the tumor, the doctor tells you are having a tumor, we will have a problem, right? And we always having the trouble. We always having the issues where it is not all the tumors are the cancerous ones. There are two types of tumors. One is the malignant tumor, another one is a benign tumor, where malignant tumors spread to other areas in the body. These are the dangerous ones. So the malignant tumors are the cancerous ones, and the benign tumors stay in one particular place. It can be removed. Okay? So that is absolutely no problem if the tumor is a benign. one can remove that easily, no issue. But the issue starts only with the malignant tumors. So these are the type of cancers. One is sarcoma. It is mainly common for the younger people. And carcinoma is mainly for the common. It comes only for the affect the elderly people. And leukemia is cancers of the blood or blood forming organs. And lymphomas, it is mainly for the, mainly affect the lymphatic system. And so this is some of the issues how the cancer enter into the system, mainly of a cigarette or long-term exposure to chemicals. Those who are working in the chemical industry or working in the lab by using a benzene as one of the solvent, and harmful UV rays from the sun, immune system diseases. So these are some of the cases where there are high possibility where cancer come into the biological system, affect the biological system, where heredity also several relatives have had cancer, or if someone had cancer at a very early age. So this is how the cancer enter into the biological system. It is the damaged DNAs will play the major role for the cancer. So once the cancer is there in the biological system, now how to diagnose such a disease? So either biopsy one can do, or endoscopy one can do, or CT scan, CAT scan one can come out with, or MRI contrast agent or MRI magnetic resonance imaging one can find out where it is exactly on the biological system, or blood test also one can do. So from this I would like to, now the cancer is there in the biological system. Now it is the responsibility to diagnosis and find out where it is. Okay. So now I would like to focus more on the magnetic resonance imaging. So in the magnetic resonance imaging, in the NMR, and in the chemistry we always talk about NMR, and in the NMR we measure the chemical shift, coupling constants of hydrogen nuclei in compounds. And in the case of MRI, we are also do the same for the hydrogen, distribution of intensity of water from proton signal. So the biological system has the water molecule, and we mainly focus on the hydrogen, how much amount of there in the particular area. Okay. This MRI mainly focuses on the intensity of the water proton signal. And the dominant image, where the imaging technique that produces a high quality images of the internal organs and tissues inside of the human body, and where the dominant nucleus imaged in MRI is proton in hydrogen. Fine. The water molecule, sorry. So this is a brief history about the MRI agents. So the MRI, it is a nuclear magnetic resonance, properties of a nuclei of the atoms, where the magnetic field required and interaction between the magnetic field and the radium frequency one can monitor. So it is where these are the two famous scientists which they discovered MR, magnetic resonance phenomenon, independently, and received the Nobel Prize in Physics in 1952. And there is a Nobel Prize on Chemistry where Richard or Ernest also received the Nobel Prize, particularly on the MRI related issue in 1991. And then there is the functional MRI developed, and they received the Nobel Prize in 2003. So just one technique. Okay, one technique, there are the three different people, three different sector. People received the Nobel Prize, just only one technique in physics, in chemistry, and also in medicine. Okay. Now, the next question is, why the people are talking about, why already there is a name, NMR is there. Why do we change the name? Why do we need to change the name to MRI? Okay, need not necessary to change. NMR is very good name. Huh? So this is how it goes. So the most likely explanation is nuclear has had a bad connotations. So if the doctor tells I am going to do nuclear experiment in your biological system, he always thinks that foreground experiment they are going to do in my biological body system. So that is the issue where NMR is always have the, nuclear is always have the bad connotations. And less likely, but more amusing explanation subjects got nervous when first talking doctor suggest an NMR. So if I am going to do NMR immediately, the people take swearing. So in order to avoid such cases, they change the name from NMR to MRI. And these are the system is necessary for the MRI purpose. You have a, one should have the magnet, gradient coil, and also have a radio frequency coil. And this is how the system works. And this is protons, this is the magnetic field. I would like to put it everything in the, at the end I will put it how the system works. This is the mechanism involved for the MRI. So a magnetic field is required, and where it aligns the proton in the magnetic field, and the radio frequency pulses where it excites the proton, and through the relaxation process, and one can get the NMR signal detection and repeat the system again and again. One can get the raw data and then Fourier transform, and one can get the clear-cut image of the disease. So it is fine. MRI, at least magnetic resonance imaging, one can identify where is the problem is. Then what is the necessary to have another agent? This is the MRI contrast agent. And this is how the agent works. This agent improves the resolution of MRI images by increasing the brightness in various parts of the body. Okay, it gives the clear-cut image. In the absence of contrast agent, it is difficult to differentiate between the healthy and diseased tissue because signal intensity is almost the same. So the contrast agents is really necessary to get the better image. If the earlier days we don't have a mobile phones, and when the mobile phone started introducing with a 1 megapixel or 2 megapixel camera, we used to take the photos. Okay, that is like a MRI. And once you started introducing 105 or 120 megapixel camera, obviously you can have the better quality. Okay, this is how the contrast agent works. Fine. So now the contrast agent is ready. It is, we wanted to find out where the disease is. So this is the agent is really necessary to have its duty, and then it has to be removed as quickly as possible from the biological system because it should not stay back in the biological system for longer period and create additional problem. That is very important for the contrast agent. So the agent should have the relaxivity and specific in vivo distribution. It has to go and particularly bind on the particular area, and in vivo stability, excretability, it should not stay on the particular place, and lack of toxicity. Toxicity also very important. It should not create any additional problem in the system. So here mainly the people use a gadolinium complex where it has a 7 unpaired electron where has the high magnetic moment, and this is how there are 7 unpaired electrons in the system with the magnetic moment of 7.9, and free gadolinium 3+ is extremely toxic, where the bound ones are plays major role to decrease the toxicity, and after it is injected into vein, gadolinium accumulates into the abnormal tissues and causes these abnormal areas to become very bright, and gadolinium is then rapidly cleared from the body by the kidneys. So this is a very important point where the contrast agent quality, what is the necessary to show the clear-cut image of the things. So these are some of the material which is available in the market. One is there are the 4 linear chain based system. Another one is a small macrocyclic based unit where thermodynamic stability, toxicity, lipophilicity, biodegradation, all those things are very important to make this kind of the complex. All these ligands are exclusively bind with the gadolinium 3+. This is one of the complex which I have shown where DTPA bound with the gadolinium 3+ complex. So these are the gadolinium available in the market. One is a macrocyclic ligand which I showed in the previous slide, or the linear molecule, where the macrocyclic ones are called, which is available in the market, it's called ProHands, where the linear ones, it is there in the Omniscan Optimark, or it is in the Magnavist, where in the starting point which I have mentioned, a Magnavist, it is the agent, MRI contrasting agent, one can use it for the diagnostic purpose, where the cyclic structure surrounds the gadolinium like crown. It binds effectively on the gadolinium 3+, so it will not move around. Okay, the cavity cyclic structure, it binds exclusively on the gadolinium 3+, go to a particular area and show the clear-cut image, and then it will not move out because of the cyclic structure. It captures very effectively and finally removed from the biological system. So, where in the absence of the contrast agent, I will give you the better image. This is only the rough image which I have given you the brain structure. Where the absence of contrast agent, one can see almost like a 5 megapixel camera image, and one can have the better image here in the presence of the contrast agent. Where the contrast agent is mainly looking for the blood flow, blood volume, blood oxygenation and perfusion, and monitor the growth and function of brain tumors. And fMRI studies are often used in planning the brain surgery. And this is how it works. It is a hugely versatile, and many more still to come, where examination of the brain and other parts of the central nervous system, breast cancer examination, high quality images, one can see the quality images very clearly where the problem is. Fine? So this is leave it. This is how the MRI works. Okay, those who are having the problem, particularly the brain tumor or any body related issue, where the other things which is not able to help, finally the doctor advises to check MRI. Okay, so the patient has the problem, something related to head, he has the problem, and whenever he talked to the doctor and he wanted to advise him to check MRI. Okay, finally this is the MRI machine, and he put him on the machine. And he fixes his head so that there is no movement about his head whenever he wanted to record the image. Fix it properly and putting him inside the machine. NMR machine, we usually take a tube and then put it inside, and here the human being is going inside the machine, MRI machine. And then the radiologist is sitting outside the window and monitor what is going on exactly, whether his brain is fine or not fine. And finally, he identified there is the issue in the human. There is some minor injury in his brain. Okay? The color illustration of the MRI, one can see where is the problem is. Okay? He identified exactly where is the problem is. And this is how the MRI works. And this is the photograph where one can clearly monitor where the problem is in the breast. So one can find out the diameter and the volume and the curve peak, everything, and locate exactly where the problem is. Okay? So this is how the MRI and the contrast agent works. And now we identified, we diagnosis the disease clearly, whether there is the tumor, in the biological system with the MRI and the contrast agent, we identified the disease. Okay? Now, it is the responsibility to remove the disease from the biological system. How do we remove a tumor in the biological system? So, the one major possibility, it is possible to remove most of the cases, it is 60% of the cases of the cancer can be removed by surgery, and wherever it is not possible, the radiation therapy or the chemotherapy or the boron neutron capture therapy or the photodynamic therapy. Earlier I mentioned very clearly that the radiation therapy or the chemotherapy is not advisable because it creates all sorts of the problem. Radiation therapy and its consequences, normal cell destruction along with the affected cells, radiation therapy, it is also create the problem. And also I discussed about the chemotherapy, a severe side effect one can see where cisplatin is able to kill the cancer, but at the same time invited various problems. And needed one complete cure after the treatment, lesser or no side effect, and easy access of the technique. So, how one can figure it out? So, the one such possible way is a photodynamic therapy, and this is how the photodynamic therapy works. A molecule which get excited, and the excited molecule transfer the energy to the oxygen, and the oxygen turn into a singlet oxygen, where the singlet oxygen destroys the cancerous cells. That is the fundamental criteria for the photodynamic therapy. So this is how the molecule, whatever the molecule, a sensitizer, whatever the sensitizer I am talking about, this is the porphyrin molecule, where our body has a hemoglobin. Hemoglobin has a porphyrin unit in the cell, in the blood. Where here there is the porphyrin framework. I will come back why are you using again the porphyrin molecule, okay? Hemoglobin has already porphyrin, and why do you want to use another porphyrin molecule for this purpose, right? So, this is the porphyrin molecule. It gets excited by the lasers and transfer the energy to the oxygen, and the oxygen into a singlet oxygen. That singlet oxygen destroys the cell, cancerous cells particularly, and removed from the biological system. So, these are some of the mechanisms involved, how the triplet oxygen converted into a singlet oxygen, and where the sensitizers transfer the oxygen. This is the sensitizer get excited, and the sensitizer, whatever the sensitizer I am talking about is a porphyrin molecule, get excited and transfer the energy to the oxygen, and then oxygen converted into a singlet oxygen, and attack on the DNA, inherited DNA cells, and oxidative damage happen, which remove the DNA cells, the affected cells from the biological system. Now, the question is, why do we have this kind of the molecule? Okay, it should be pure and known and constant composition, and it should be within the range of 600 to 800 nanometer. Your sensitizer, whatever the molecule which I am talking about, your porphyrin molecule should have the facility of observing the light up to 600 to 800 nanometer. If it is in the biological system, it is the water solubility, preferential accumulation on the targeted tissue, and a negligible dark toxicity, oxygen dependency, and of course high photochemical reactivity. But as of right now, none of the sensitizer meets all the above criteria. Whatever the molecule which is available, whatever the medicine which is available, porphyrin based medicine which is available, not meet all this kind of the criteria, and many investigators have turned their attention to those for some favorable properties. Whatever the major ones, they have taken it, and used it for the further purpose. And now the next question comes with why do we need the molecule to should absorb from 600 to 800 nanometer? Okay. The major issue here is the melanin. The body has a melanin which absorbs around 300 to 500 nanometer. And the hemoglobin which absorbs from 400 to 600 nanometer. So obviously one should have the better absorption from 600 to 800 nanometer. Okay. Okay, if it is 800, above 800 also it is okay. Why not possible, right? The next question comes up, okay, 600 to 800, it's okay. Above 800 also it is necessary. One should, the next question comes, okay. The problem is, therapeutic window one can fix from 600 to 1000 nanometer. However, above 850 nanometer, photons have lower energy, do not participate in photochemical reactions. So, the better ideal window is from 600 to 850 nanometer. And this is how the system goes. This is the photosensitizer, whatever the porphyrin molecule which I have talked about. A photosensitizer injected in the biological system, it goes to the entire system. Of course, wherever the person has the shoulder pain or shoulder problems or shoulder the cancerous materials are on the particularly on the shoulder area, one can use the laser light so that the molecule get excited and convert the particular area oxygen into a singlet oxygen. That singlet oxygen destroys the cancerous cells. Now, in this case, which I have mentioned about the laser, which is outside the system, absolutely no problem. There is the periphery on the body, absolutely no issue. Now the problem is inside the body. How do we monitor? For such cases, isobagus light distributor or radial light distributor one can come out with, which goes inside the particular system, and accordingly you can give the light source. And a lung balloon or light distributor, these are the things which goes particularly on the particular area. If at all if there is the problem on the kidney related area, go to the particular area and gives the light so that the molecule get excited and the cancerous cells be destroyed on the particular area. And this is one such cases how the people have used for this purpose. A thermoporphyrin is, I will give you the exact structure of the thermoporphyrin. Okay. So this is a 68-year-old person with an infiltrative squamous cell carcinoma, a cancerous disease, and this is how the initial period it was like this, and after PDT examination it cured after 3 months by using the PDT treatment. And this is another such example where the extensive chest, and this is the breast cancer related after the surgery. Also it is not possible to get it cured, and for that, in order to avoid such circumstances where the person is put under narcotics for almost longer time so that there is no pain for the particular area. So she was also under treatment for almost with a PDT, and after 3 months she get it relieved from the problems, and this is mainly of the PDT which plays a major role. After that she no longer required narcotics for the pain control. So now I talk about the PDT, where what are the sensitizer molecule available in the system. These are the molecule which I would like to highlight, and one is porphyrin and thermoporphyrin, lutetium hexaferrate. These are the molecule which is commercially available as of right now today, and this is how it goes. Veratoporphyrin, it is in the commercial name of Isodine. It is available mainly for the age-related macular syndrome and skin cancer. The people are using it. Mainly, this molecule observed at 690 nanometer. I told you 600 to 800 nanometer is the ideal thing. And here also, pyrrolidine, this is also used for the various cancer treatment. And this is another two molecule. This is thermoporphyrin, which I told one of the squamous cell carcinoma disease. And this is the trade name is called Foscan. And this is also used for the cancer purpose. And then this is texaferin, where the scientist who synthesizes the material is from Texas, where he has kept his name, kept the molecule name as texaferin. And where the molecule exactly observed, molecule observed at 732 nanometer and mainly used for the various diseases. So, what is the advantages overall altogether? Now, we have these are the advantages for the main for the photodynamic therapeutic agents, where avoid systematic treatment, particularly treatment occurs where the light is delivered, minimum side effects, selective targeting, it's a low cost, repeatable, and when surgery is not applicable, one can use this kind of the technique, possible to solve the cancerous cells disease from the biological system. And at the same time, there are side effects. There are side effects with the milder ones, however, not as compared to the cisplatin. So the overall, I would like to finally summarize. In the current millennium, PDT is going to be one of the important modalities in medicine. So with this, I would like to end my talk, and what I have discussed today, talk about the cancer, talk about the cisplatin, and talk about diagnosis the cancer, and also how to eradicate the cancer from the biological system, from the body. Okay. With this, I would like to take this opportunity to thank you again for the kind attention.
Thank you, Professor Srinivasan. I would like to request Director Professor Sudhakar Pandit to come up and offer a token of gratification to Professor Srinivasan. One for social media. Before we conclude for the day, let me take the honor of inviting Professor Sudhakar Pandit to speak a few words.
Okay, let me congratulate you all for the 11th Foundation Day of NISER. He asked me to say a few words, but most of the words he has already told in the morning. The question was that whether we will celebrate this Foundation Day or we could do as best we can, and we went for the latter thing. And specifically, I didn't like going in the same tradition, half done, half not done. You request someone to come and address us, give the Foundation Day talk, but they seize the opportunity by telling that I can't come, but I will give you a virtual talk through the Skype or video. That I wanted to avoid, and I feel happy that we could find our in-house speakers, and sitting through these two talks, I don't think we missed anything. People of eminence in science, etc., the type and quality of the talks, I have heard in the last couple of years in this room, and today's talks were no way less compared to them. So I thank both the speakers, Professor Mahanti and Professor Srinivasan, and for giving these talks. And I'm proud of them. So sometimes we don't have to worry about getting the speakers, etc. We can look within our campus and carry on. So that's the best, and I'm thankful to them they agreed. And thanks to the academic section, Dean Academics and Associate Dean Academics for their effort to organize this meeting. And let's see what waits for us in the next year, 6th September 2021. Thank you all.
Hope we have a corona-free year next year. Even though we don't have a packed house here, the efforts that went into organizing this is almost the same. So I would like to put on record my thanks to the entire academic section for this. People from Works department, Dilip, Savagya, Shankar for ensuring that we didn't have any problem with the electricity and AC. All of you who took the pain to come down here and be here, because without seeing anyone in the front, no speaker would like to kind of get that impetus to talk about anything. And all those who are logged in, thank you so much for being there. People who worked in the background for making the arrangements, starting from our videographer Santu, Saikat and his associates, Somnath, Abhay for making, ensuring that housekeeping people are in job. So I sign up with this, and we look forward to having a better as an infrastructure and logistics, not talk-wise, next year. I also thank my predecessors, Dr. Binod Sahu and Professor Muruganandam, for giving us the legacy to carry forward. Thank you, all of you.